Welcome everybody and thank you for coming to this talk. Today we're going to talk about how to push your streaming platform to the limit. And before we begin, let me introduce myself. So my name is Elad Leev. I'm a staff engineer at Dojo, a fintech company from the UK. And I'm mainly working around everything regarding to distributed systems and data streaming. So obviously it's going to include Kafka, Flink, and other services like Debezium, Kafka Connect, and so on. To begin with, I want to start with a quote from a book by this guy, a computer scientist named Jim Gray. And usually I'm a huge fan of those books from the 80s, from the 90s that are still relevant even today, 40 years later, which is kind of amazing. The book itself contains a lot of gems, especially around how you measure system performance and what do you do with it. But the bottom line is that measuring a system performance is hard. There are no magic bullets. If, for example, we will take Kafka as, again, one of the biggest messaging platform, our use cases may vary based on message size, based on the traffic patterns and the different service that is communicating with Kafka, and even based on configuration that we set to the Kafka clusters. So the results that we will get from the same machines might be completely different based on those parameters. So when we evaluate a new technology, usually what people do is just to put most of the weight on the total cost of ownership, which makes sense in a way, but we can't really rely on our vendor's performance benchmark because essentially your vendor benchmarks are just a marketing job. So as data-driven professionals, that's not something we can trust, right? It's not something that we can believe, and we can't just, assume that our system will behave normally as we scale up and down our systems, especially on events like Black Friday, Cyber Monday, and those kind of events where our system are pushed to their limits. We need and we must know what is the limit of our system, and for example, knowing how much our system can handle, how many requests per second, how many users it can serve, and so on, and especially knowing what is the limitation factor, it might assist us later on in stuff like preventing maintenance, in stuff like capacity planning, and even to eliminating toil, because then we don't need to take actions when the clusters start to misbehave. Now, when it comes to a failure of a system or a limitation of a system, especially when it comes to performance, we only have 4 pillars of failures. So it will either be the disks, the memory, the CPU, or the network. Most of the times, this will be the issues. Now, if we want to test our systems, how can you know what is a criteria of a good benchmark? How do you know how to define a good benchmark? So first of all, it might sound obvious, but when running our benchmarks, we can't do any tricks. We can't just use, faster machines or more pods. We can't make any JVM tweaks or even change to a completely different JVM or anything like that. We need it to be as similar as the environment that we are testing against, let's say production or anything like that. And even if it will cost us more money to spin up the exact same environment, it's super crucial to our benchmark because this is what we are testing against. So no special tricks. And you need to remember that it's not a game. We are not trying to, optimize for the best results or to optimize for a specific use case or anything like that. We aim to get the most accurate result from our benchmarks. Obviously, metrics are crucial for the success of the benchmarks. So if you don't collect your system metrics, first of all, start by doing it. Put everything on a fancy dashboard, especially focus on those 4 pillars that I mentioned. Again, CPU, disk, network, and memory. And make sure that you collect and have a dashboard that represent all of them, because during the execution of the benchmarks, we want to look and to log how our system behave using those dashboards. Now, we need to aim for the peak of those systems, or better yet, we need to add some sort of a buffer to it, because we do need to expect the unexpected. This is a famous quote from Werner Vogels, the CTO of AWS. He has a lot of amazing blog posts, so definitely check it out. But one of them is that failures are given. Everything will fail eventually. It can be, again, your network card, it can be the disk itself, the VM that you are running on, the Kubernetes pods, or anything like that. Failures are given. But the problem is, and this is one of our challenges as software engineers, is that we still need to serve our users during peak times, even if we will lose one or two of those machines. So on our benchmarks, we need to aim for that point and to add a bit of a buffer. So for example, you should aim for the n-1 or n-2 when you're running the tests. You need to make the benchmark as scalable as possible because, like we mentioned, our systems is essentially a living organism. Our clusters and systems tend to scale up and scale down based on different factors and based on different events. And we need to embrace the changes. So we need a framework that will allow us to add more executor to test our system and to put more weight on our system. And we need the ability to scale it up and down. Last but not least, simplicity is key. Like everything in life, don't try to overcomplicate things. The benchmark must be understandable. The benchmark must be reproducible, because otherwise it will just lack of credibility. Because I already saw a lot of vendors that are, promising a lot of big promises, like network between two hosts, which is faster than the light and stuff like that. So just keep in mind that you need to keep those benchmarks as simple as possible. Document the process, document the key results, document all the parameters that you set in your benchmark and so on. And again, keep it simple. Now that we understand what is a good benchmark, what exactly are we looking for? So one of the best methods that I know to evaluate a system is the use method. Use is an acronym for utilization, saturation, and errors. And the method itself aims to solve about 80% of the problems with 5% of the effort. So for example, the same as a flight attendant, which has some sort of an emergency checklist, we will have the use method to test our system. The test itself and the system is a simple system, a straightforward and complete way to test our system with almost no effort. So again, for each one of those components, we should look for the utilization, for the saturation, and for the errors. So for example, when it comes to CPU, we should look on metrics like the load average, the user utilization. When it comes to our network, so obviously we want to look on the available memory. We want to use if it's a JVM-based system, so obviously we need to watch for the GC, for the heap, stuff like that. And same goes for networking and disk. So again, for each one of those components, make sure that you're collecting the right metrics, make sure that everything is in the dashboard, and make sure that you are looking on the utilization, saturation, and errors. So how do we benchmark our streaming platforms? Obviously, there are many way to test our systems, and the same as we have many ways to test the system, we have way too many streaming platforms nowadays. Obviously, Kafka is one of the biggest ones, but you have other competitors like NUTS, Pulsar, and RabbitMQ. And the last few years, you saw a lot of Kafka compatible systems like BuffStream, Red Panda, and others. So yes, we can use the old good JMeter to test our systems, but not all of them are JVM based. So we need to find another solution. We can use the system specific benchmark tools. So for example, Kafka itself is baked with a performance test script that you can run against your system. And the same goes for RabbitMQ and NUTS, which has its own benchmark utility. But as I mentioned before, one of our goals is to seek a system that will be easy to move to a different system. Because, for example, today we use Kafka, but in a few years, maybe we will use a different system. So we need to use the same framework to different system. Again, the landscape is changing fast and we need to adapt. Exactly for that use case, we have a project from the Linux Foundation. It's called Open Messaging Benchmark Framework. It's in cloud native, so it's running on Kubernetes. It's a vendor neutral, so no one is really affecting it. And it has an open specification. So for example, if you will have another or different system, you can just, implement some interfaces and test against your system. And it will allow you to test different distributed messaging systems like Kafka, Pulsar, and others. This framework itself is composed out of two components. The first one is the OMB driver. OMB stands for Open Messaging Benchmark. And the driver itself is the brain, is the main components. It is the one that will orchestrate all the different tasks. It's the one that will communicate with your cluster. So for example, this is the one that will actually create the topics, for example, if we are talking on Kafka. And the other component is the worker. So for example, this is the benchmark executor. This will put all the load on our cluster, and we will have a single brain, but a bunch of workers. This is how it should look like pretty much. Like I mentioned, everything can be running on Kubernetes or on VM based on you. You can decide. And the benchmark itself will run like yet another consumer and producer on our system. It will communicate with our clusters and will mimic the same behavior as our clients. So for example, if you're trying to test one of your most critical services, let's say that you have 10 consumers and 10 producers, make sure to do the same thing with the benchmark. This is how the example configuration looks like. On the left side, you can see Kafka. On the right side, you can see Pulsar. Obviously, we start by picking up the right driver, which is, like I mentioned, the implementation itself. You define the basic configuration, stuff like where is my brokers, where is my cluster, what is the ports, stuff like the common configuration to our consumers and producers, and so on and so on. Obviously, we can define the producers and the consumers. So you will need to do research in advance, and you will need to make sure, for example, what is the most common used configuration on your environment. If you provide your developers an internal client that you define, so it's easier to do it, but if you don't do it, then you will need to do some research in order to find the right values, and then you can just specify them here. And just remember that everything regarding to your producer and consumers will affect the end results, which is stuff like latency and so on. So make sure to do the right research. Same goes for the consumer. You can define what is the queue size, if you want to auto-commit the offsets in Kafka case, and so on. When it comes to the workload file, so this is essentially the way that we define how much pressure we put on our system. So we can define the rate, we can define the amount of topics and the amount of events that we want to send. And again, if you are trying to optimize for a given service, let's say your most critical, transaction processing service, so you should look for the average message size of that service and try to find the right workload file to send. Because like we mentioned, the message size may affect the result of the benchmarks. So again, this is how you define the workload files. This is how you define the producer rate, and the system itself, the framework, will try to optimize to the max sustainable rate. And again, we will use it later on when we run the benchmark. And then we simply run the benchmark. You will see that the brain itself is running a bunch of pods. If you're running it on top of Kubernetes, that will execute the workers. It will scale down, scale up based on the workers that you defined. Again, each one of them will be either a consumer or a producer. You will see the lag going up, the lag going down, and so on. And it might be a bit outside of this scope, but run those benchmarks a bunch of times using different configuration. But in one of the test scenarios that you're doing, make sure to kill one of the brokers, because you want to see the impact or your clients. So for example, you want to look on the dashboard and you can see that the latency all of a sudden spiked, or all of a sudden something is wrong with your cluster and so on. So as part of the metrics of your tests, make sure to test a scenario where you lose one of the nodes in the cluster. After we run all the benchmarks, we will get the results. It will be in a single file, and again, we will have the dashboards, but what insights we are trying to get from those tests. So as part of the result, we will get the average latency, which is crucial for us because this is essentially the contract that we can offer our users in terms of end-to-end latency during peak times. So for example, if you have a service which is sensitive to latency, and you can see that you tried a bunch of different configuration and none of them actually match the requirements, maybe either you can try a different configuration or even try a different solution, because this is what good looks like. And again, just you need to remember that all of the different configuration might affect those results. So for example, compression rates like gzip, std, snappy, those kind of compressions might reduce the network overhead, and stuff like AX in Kafka might improve the durability but will increase the latency. So just make sure to test different scenarios and different configuration against your system. Obviously, like I mentioned, we will have the dashboard, let's say in Datadog or Grafana or whatever you use, but as part of that scenario, we will manage to test it against a critical workload. So for example, if something will be broken during those peak times, we will know it in advance and we won't lose our vision during an incident. So as part of those benchmarks, we will see if something is broken with our monitoring services. The next one is potential bottlenecks. Obviously, like we mentioned, CPU, disk, memory, and network. Maybe we will discover something about it. Maybe we'll discover that one of them might be a potential bottleneck in the future. And then, for example, if we discover the disk is the limiting factor, maybe we can set an alert to a lower value, and that will give us some time to react in advance instead of reacting during an incident and during peak time. So this is one of the crucial things about running those tests. The next one is scale-up estimations. So like I said, you're going to run your benchmarks again and again. And in some of those cases, you're going to add some nodes to the cluster and to see how much your performance gain from another broker or another node. So you'll get some sort of estimation on the impact of adding more nodes to your cluster. The last one is consumer and producer configuration guidelines. So like I said, you're going to run your benchmarks again and again. By the end of it, you will have some sort of metrics of system recommendation. So maybe you can put it on either a fancy dashboard or a nice documentation, and you can show your users. So for example, if you specify parameters X, let's say ACK equals 0 or something like that, then the predictable throughput will be Y. And the latency will be something else. So you can have this nice metrics that your user can use in order to define what is the right configuration for them. This is it basically. I hope that it gave you a bit of an idea why you need to run those tests. And you need to remember that fine-tuning those systems and those streaming platforms are a long process. It depends on many different aspects in the system itself, like the configuration, and we need to run those tests and observe in order to learn. And to do that, the only options that we have is basically to push our streaming platform to the limit. And that's it. Thank you.